Hello, cosmic wanderers and algorithm aficionados. Welcome to PaperLedge, the podcast that transforms dense academic research into engaging, jargon-free audio experiences. I'm Ernis, your friendly neighborhood science enthusiast. Today, we're diving into a fascinating paper titled, "When Do Transformers Learn Heuristics for Graph Connectivity?" It's a mouthful, I know, but trust me, it's pure gold. Now, imagine the vastness of the cosmos, a boundless network of stars and galaxies, each connected by invisible threads of gravity. That's not unlike the graphs these researchers are exploring. Intricate webs of nodes and connections. Except instead of stars, we're talking about data points, and instead of gravity, we're talking about relationships between them. The big question they're tackling? It's a real head-scratcher. Why do these fancy transformer models, the same tech that powers large language models, sometimes take shortcuts, relying on simple tricks instead of learning the real, underlying algorithm? Think of it like this: you're teaching a computer to find the quickest route between two cities. The right way involves learning about roads, distances, and traffic patterns. The shortcut, just guessing based on the city's population sizes, works sometimes, but definitely not reliable. Let's step into our mind palace, shall we? Picture a sprawling, futuristic city. Each building represents a key concept from this paper. The first skyscraper we encounter, capacity. This isn't about how much coffee you can drink, but instead, how large of graphs can the model solve correctly. This paper's argument is that transformers, despite their power, have limitations. They can only truly understand graphs up to a certain size or complexity, which the authors define using something called diameter. Above that capacity, the models resort to heuristics. The researchers dive deep into this, both theoretically and with experiments. They use a simplified transformer architecture they call the disentangled transformer. The disentangled transformer is just a fancy way of saying that the model architecture is easier to interpret than typical transformers. They prove that an L-layer model, where L is the number of layers in the model, can solve graphs with a diameter of up to, but not beyond. Now, what exactly is diameter in graph terms? Imagine you're in a social network. The diameter is the longest chain of friends. You need to connect any two people. A small diameter means everyone is relatively close. A large diameter? Well, you might need to go through dozens of connections to reach someone. The interesting part here is that the learned strategy hinges on whether most training instances are within this model's capacity. Within capacity graphs, diameter is less than or equal to drive the learning of a correct, algorithmic solution, while beyond capacity graphs drive the learning of a simple heuristic based on node degrees. Fine, yeah, I guess. The point is, this paper is a big deal. Here are the key discussion points. Key discussion point 1. Non-asymptotic capacity tied to diameter. Imagine the transformer model as a vast, unexplored galaxy. Each layer of the model is a star system, capable of processing only a certain amount of information. The researchers prove a capacity theorem that depends on instance difficulty, characterized by the graph diameter rather than only on the number of nodes. They show that an L-layer model solves connectivity on all graphs with DIA is less than or equal to. This capacity is tight and exact, which they empirically validate by training disentangled and standard transformer models. Key discussion point 2. Algorithm, heuristic decomposition. Let's visit another building in our memory palace. This one is a laboratory, where the researchers dissect the transformer to see what makes it tick. They prove that the learned weights for a disentangled transformer are a superposition of an algorithmic and a heuristic channel. The algorithmic channel is responsible for multi-hop composition, matrix powers of the adjacency matrix, while the heuristic channel determines connectivity based on node degrees. Picture this as a cosmic dance, where one dancer follows precise steps. The algorithm, and the other, improvises, based on the crowd's energy, the heuristic. Key discussion point 3. Training dynamics. The training dynamics reveal a sharp dichotomy driven by the data distribution. For graphs within the model's capacity, diameter is less than. Population gradients. Suppress the heuristic channel and favor the algorithmic channel that implements matrix powering. Conversely, when the distribution contains a significant share of beyond capacity graphs, diameter is greater than. The gradients strengthen the heuristic channel, promoting the simple degree counting shortcut. Imagine the model as a student learning from examples. If most examples are easy, the student masters the real algorithm. But if too many examples are complex, the student gives up and relies on simple tricks. Key discussion point 4. The data lever. The researchers propose a direct mitigation strategy they call the data lever. By restricting the training data exclusively to within capacity graphs, they boost the algorithmic component and improve out of distribution robustness. This is like giving the student a carefully curated set of problems that gradually increase in difficulty. Okay, fine. So, what does this mean in practice? Their experiments confirm the effectiveness of this approach, showing that it boosts the algorithmic component, improves out of distribution robustness, and that these benefits transfer successfully to standard transformer models. The key insight here is that the model's capacity needs to align with the complexity of the training data. In conclusion, so what is the big picture? By pinpointing precise breaking points of transformers and how the training data influences the learning of generalizable algorithmic components versus brittle heuristics, the analysis yields a strategy to reduce dependence on heuristics via the data lever, demonstrating that the theory also has some prescriptive power. And that, my friends, is the essence of this intriguing paper. It's a cosmic reminder that even the most powerful tools can be misled by shortcuts if we don't carefully calibrate their training. So, next time you're marveling at a large language model, remember that it might just be guessing based on population sizes instead of truly understanding the roads and traffic. This was Ernis, and we'll see you next time.